Hello, good morning, good afternoon, good evening, wherever you are. Welcome to another session of at SNT 2021. Now we will be having an oral session on the atmosphere and its dynamic, topic 1.1 in the program. And Paulina Bittner and myself will be convening this session today, where we have six speakers. And I just want to say a word to them because I inverted the order, of course, when we were preparing this talk just a few minutes ago. So we'll start with David Viersema, and then of course we'll follow the order that is in the program. And we were supposed to have 7 talks, but one of the speakers had to excuse himself, Professor Sergei Kulishkov, because he could not make it today. And so we'll have a bit less of propagation modeling. I'm sorry for the viewer that wanted to see it, but we'll have a lot of interesting talks going from modeling the atmospheric transport to looking at volcanic eruptions and microbarom activity, and also going a little bit to the southern hemisphere with looking at what is happening in around Bolivia and with the Bolivian station in particular, and some research led by the institute over there. So I will not take too much time. I think we'll be starting right away with David Viersema, but I just want to remind all of you viewers who not hesitate to post questions. We will be taking questions if time allows at the end of each talk. So don't wait to post your question. If you have one, just post it, and we will be asking the speakers to answer at the end of the talk. So we'll have, I think, 4 live speakers and two recorded talks that will be happening, but all the speakers are here and can answer questions live, so we'll be able to do it. Of course, if we don't have time for questions, don't hesitate to go to the speakers' presentation that are available under the session in the program and ask your question in the chat. We will ask the speakers to go there and monitor the chat, monitor questions, so that they can answer you, and we can eventually even have some meeting with them in some of the video rooms we set up together for you during the week. So I spoke enough. Let's move on to Dr. David Viersema, who will be the first speaker today, talking about modeling atmospheric transport and dispersion over complex terrain. So, Mr. Viersema, you have the floor.
Thank you very much. Excuse me. Thank you very much. Today I'd like to talk to you about modeling atmospheric transport and dispersion over complex terrain. This is work I've done in conjunction with several at Lawrence Livermore, including Lee Glasgow, Akshay Gordon, Catherine Lundquist, and Sonia Wharton. So we are primarily interested in doing high-resolution atmospheric modeling over complex terrain because of microscale processes that are driven by regional and synoptic conditions. These include fire weather, hazardous releases, wind energy, and air quality, all of which are critical importance for everyone here, as well as especially in my home state of California, where we already have some severe wildfires starting again this season. At Lawrence Livermore, we have NARAC, the National Atmospheric Release Advisory Center. This is a group of scientists and researchers that can gather at a moment's notice in order to provide 24/7 emergency response for airborne hazardous releases. An example of some of the briefings that can be produced by NARAC is on the right figure here, and these can be produced from a variety of models that can be run very quickly or take more time and run on high performance computing systems to give a higher fidelity solution over the long run. As I mentioned, we have a suite of models. These range in computational cost and complexity. On the simple end, we have models that are Lagrangian in nature, such as ADAPT and LODI. And then we have in the middle Reynolds average Navier-Stokes equations, where the effects of turbulence are completely parameterized. And the most complex models we run are what's known as LES, large eddy simulation. These are where we resolve the largest scales of turbulence and parameterize any small scales. So running through some of those models in a bit more detail, ADAPT, the atmospheric data assimilation and parameterization tool, takes a numerical weather prediction forecast from any of the major sources in the world, and then we also use any observations that are present, regrid that data while enforcing mass conservation, and then interpolate it in time to whatever interval we're interested in, such as hourly intervals. Each of these times will take about 1 minute of computation. And once we have that regridded field, we pass it off to LODI, the Lagrangian Operational Dispersion Integrator model. And with LODI, we solve for the fate and transport of hazardous materials. And we can include many different types of sources, ranging from power plants to any detonations or dispersal devices, fires. And then once we have those sources, we can include multiple types of materials. Each of the sources will consist of source particles in the model. These can range from roughly 500 to 100,000. And the simulations for the fate of those particles will take around the order of minutes to complete. When we move upwards in complexity, we go to computational fluid dynamics codes, such as the AOLOS model, which has been heavily developed at Lawrence Livermore. And this CFD code can run on a laptop all the way up to a high-performance computing system. It is also tracking for the fate of these particles. However, now that we're running this high-resolution CFD in the background, we can include realistic complex terrain, such as urban centers. And then the highest complexity that we run in-house is called the Weather Research and Forecasting Model. This is actually an open source and community developed code. It's maintained by NCAR, the National Center for Atmospheric Research. And just like AOLOS, it's capable of both running in the mesoscale at coarse resolutions as a Reynolds average Navier-Stokes code, or as a large eddy simulation when we move to high resolutions. And because of the open source nature, this code, it has numerous atmospheric physics parameterizations because of all the development it's seen over the years and the wide user base. It's important to note that because it's capable of both mesoscale and microscale simulations, we can do what we call multi-scale simulations, where we go all the way from the coarse resolution domain down to the very high resolutions, where we're resolving turbulence and small-scale flow features. And to do that downscaling, we use a technique called grid nesting, where a parent domain run at a coarse resolution has a higher resolution child embedded inside of it. and that child domain receives information at the lateral boundaries from the parent. We do this several times in succession, as shown in the bottom right corner, and we have this telescope of nested grids that leads us down to our highest resolution model of interest. At Lawrence Livermore, we have several different major developments of the WRF model, and these include introducing some interesting new physics to the model. This is a development where we're trying to look at a detonation and the hot bubble of gases that is the result. On the left, you can actually see a test of the new code, and the cloud formation is shown along with precipitation that's being predicted in blue and deposition contours on the surface. We also, in order to see how well this code is doing, compared to some of the historical test footage, which is shown on the right. And this is actually from 1953, so it's surprisingly good agreement given the conditions that we have. Another major development at Lawrence Livermore is the introduction of an immersed boundary method. And this is an alternative gridding technique that allows us to run with highly complex terrain in the model that normally the WRF model would not be able to accommodate. This could be mountainous regions or in the simulation shown here, an urban environment with steep building faces. This model will enforce a log law boundary condition along the complex terrain. And we typically run it at very high resolution, such as 2 meters in the simulation shown. This particular animation is from simulation of the Joint Urban 2003 field campaign, which took place in Oklahoma City. And by using this immersed boundary method, we were able to achieve some very remarkable skill scores versus the sensor network for this particular controlled release. However, we're not satisfied with the current data sets that are out there, so we are attempting to collect some new data from experiments in complex terrain. More recently at Lawrence Livermore Site 300 in 2019, we went out and deployed quite a bit of instrumentation and did some shots of high explosives in order to look at the plumes and the fate. We deployed 15 cameras, several gas samplers, a few LiDAR systems, and then Pacific Northwest National Laboratory also came out and implemented a laser spectroscopy system in order to evaluate concentrations in the plume directly above the firing table. Prior to that experiment, we ran some of NARAC's day of simulations. These are fast-running codes that we started several hours prior to the shot, and then we were able to take the results with us and adjust our sensor placement in order to better capture the plume. After the fact, we ran some high-resolution WRF LES simulations to gain more knowledge about what was going on in between our sensors. And the simulation that I'll show you some results from here is a 4-domain simulation that goes down to 10-meter resolution at the highest domain. One of the problems that we were seeking to answer was we had a non-detect at one of the gas samplers, which was seen to be inside of the plume by the camera nearest to it. The gas sampler is shown in the left figure as this green star. And we were seeking to gain more understanding of whether or not the plume passed overhead of the sampler or if the sampler was malfunctioning. And in order to get that, we ran this very high resolution simulation. And what we ended up finding was the sampler was actually inside of the plume and malfunctioning. And so on the right, you can see time series of what the sampler would have experienced. And on the bottom right, the gray shaded regions are times where the sampler was actively sipping air and should have had a detect. And with that, I think I'm near the end of my time, so I will conclude by saying that at Lawrence Livermore, we have a range of models. NARAC is running them all. They go from Aeolus and up to WRF. With that, thank you very much, and I'll take questions.
Thank you very much for this interesting talk. It was nice to see what you are doing at Lawrence Livermore and all the capabilities you've been developing. We have a group of shy viewers online, so so far we don't have any online questions, but we can maybe have a few questions to you, just to know what is next with your actual research. What will you be doing? Will you continue to develop your capabilities and some of the code? Will you continue to do some of the some new measurement campaigns to validate your code? And I also wonder, what is the certainty that the sensor actually did not work in the last case? Did you validate the malfunction of the sensor, or what is it only based on the numerical validation that you have this conclusion?
Yes, thank you. So talking about the future of the research, we do have several more field campaigns that are being planned at the moment, and these could include possibly more field campaigns at Site 300, which is very rugged terrain. However, we're looking at other options for location as well, and we hope to expand our sensor network now that we've done this more basic set of simulations and this more limited field campaign. We hope to expand it for the next one. And then talking about the gas sampler itself, we did evaluate the sampler, and it was working as intended when we evaluated it. So our best hypothesis is that when the bagged samples were taken to the laboratory, that there might have been a laboratory mix-up, or perhaps the mass spectrometer did not function as expected. So we're not exactly sure where the error took place, but the evidence seems to indicate that the sampler or the processing of the sampler was the problem.
Building on this, I see that there is a question in the chat. And so I guess you already kind of answered it. And the question was, did you place the instrument in the area that was the model predicted the detection as well? And so you have additional lack of detections in other areas?
Yes, so we had several other sensors that both had detects and non-detects. So each of the samplers has a carousel of different bags that it fills, and it rotates from bag to bag over time. And so for many of the samplers, we were able to see a signal from the plume at certain intervals, and then a non-detect following once the plume passed overhead.
And I see one of the other speaker is asking a question in the chat here from so Benoit 10 is asking if you're also interested by gas phases only, or are you also looking into particles with your modeling?
So in this simulation, we did not consider large particles with ballistic trajectories. However, we have capabilities to do so. So we can look at ballistic particles, or all the way down to smaller particles that are unaffected by obstruction. So we can have pretty much whatever size particles you can imagine in the models. But in this particular simulation, we only considered the tracer gas, so looking at carbon monoxide.
Okay, so I think we'll take one last question before we move on to the next talk in an effort to keep the time. And the question is from the chat. In the case of CFD urban modeling, how do you obtain urban orography for various cities so that it is up to date to provide accurate boundary conditions in the event of an operational response?
Yeah, so we have a system that pulls data from multiple sources every single time they're updated. So we do this hourly, and we have a large repository on site that we can pull from at a moment's notice. So we have a multitude of sources as well as observations that are all stored locally.
Good. Thank you. Thank you very much, Dr. Viersema. It was really nice having you today.
Thank you very much. And please reach out if you have any further questions.
Yes, I want to invite all the viewers. If you have more questions that you didn't have time to ask or want to ask later, go visit the contribution of David Viersema on the T1.1 oral session today, and you can post your questions there. So with this, we'll be moving to the second speaker with Dr. Kathleen McKee, who will be presenting the work of a large group of researchers on multidisciplinary characterization of the June 2019 eruptions of Raikoke and Ulawun volcanoes using remote technologies. And so, Dr. McKee, you have the floor. We can see your screen, Kathleen, but we do not hear you. Kathleen, we do not hear you. We see your screen that is shared, but we do not hear you. This was not working a few minutes ago, so I'm sure it will work again. It's really a microphone issue because we can really see well the screen and you share. We see the first slide right now, but we just have no sound. I think what I would propose is maybe, Kathleen, you have to go out of WebEx and reconnect. That's the only way I see that maybe the sound will come back. If you, because we see well the screen, we just don't hear you. It's really a microphone issue. So bear with us. We're having technical difficulties. That's the beauty of being in a virtual conference. But I think Kathleen will join us very soon again. And I think she will be able to present her talk when she's back.
Hi, can you hear me now?
Yes, we can hear you.
Oh, perfect. That's so weird. It was working earlier. Okay.
It's all fine. I'm glad it's resolved. It's the most important.
All
Good.
right. Yes. Okay, and you can see slides.
We can.
Great. So hi, I'm Kathleen McKee. Good morning, good evening, wherever you are in the world. Today I'm going to be talking about a multidisciplinary characterization of these two eruptions. One, Raikoke is a closed system, so it doesn't degas, normally. And then Ulawun, which is an open system that regularly degasses. And these are both large eruptions, about 4 or 5 days apart in 2019. So let's get started. So volcano acoustics is particularly critical in volcano monitoring, here's a sort of a nice figure of all the different types of signals that we observed from volcanoes, from tremor to explosions to these two time series on the bottom, which are large, what we call Plinian eruptions. That this is over about 13 hours. This is an example from Tungurahua in Ecuador. And infrasound is particularly critical for detecting, locating, and characterizing eruptions, because volcanoes are often grouped together or in long lines. So figuring out which one in particular is erupting is important for mitigating the hazards from the volcano. And for volcanoes that we don't have monitored or obscured by clouds, infrasound is really critical for confirming when we actually have something interacting with the atmosphere. So really useful tool used by many volcano observatories around the world. So when a volcano erupts, our sort of initial questions are, what volcano erupted? When did it start and end? And does the eruption change through time, and how? Is it increasing in intensity? Is it decreasing in intensity? Because these are all critical for mitigating the respective hazard depending upon the type of activity. So why do we care about volcanoes? In addition to populations that are immediately in the vicinity of the volcano, from a global perspective, airplanes are at the greatest risk. I think most of you sitting in Europe will remember the 2010 eruption of Vaðafjallajökull in Iceland that shut down air traffic across Europe. And so here in this figure on the right, you can see flight patterns. And you can see all the flights between North America and Europe that go right over Iceland. And then all the flight patterns going between Asia and North America that go over all the volcanoes that are in Japan, Russia, and the US. So it is really critical for us to know, especially for those that are in those in Russia and Japan that are not populated, really, and have varying monitoring. It's critical for us to know if those are erupting, and where, in order to reroute airplanes. So this is a sort of critical for mitigating that hazard. All right. So Raikoke is a volcano in the Kuril Islands. This is the island chain between Japan and Kamchatka, Russia. And it erupted on 21st of June, 2019. And we detected it mostly with the IS-44 array in Kamchatka, as well as two other more remote arrays, which I'll show you shortly. And for the volcano enthusiasts, this is just north of Serashev Peak, which had a large eruption about 10 years prior to this one. So hopefully this will work here. This is a time lapse of Himawari images of this eruption overlain with a sonification of the infrasound data. So now we can look at that time series that we just listened to and observed. So in this main figure, we have the infrasound data from IS-44. And then the colored, they're actually dots, but mostly show up as bars here, are the colored bars there indicate when we have detections. So as you saw and heard in the video, we could see pulses to start. So we had 6 pulses that vary in duration from 10, 15 minutes to 45 minutes, and then a long sustained plume here, and then some additional pulses. And if the sound worked, hopefully it did, you could hear it got very windy here in the end as well. So just note the wind noise is a constant. We use IMS-VAS, which was a code developed by Matoza and others to take back azimuths from and estimate a source location. And so with that, using IS-44, 45, and 30, we get an estimation right near Koke, about 79 kilometers from True, and given our array distances, this is a pretty good rough estimate of the source location. Now for a little bit on the characteristics of this signal, I'll highlight here in our frequency content on this lower panel. You can nicely see those initial 6 pulses, and then the long, large eruption, which we refer to as a Plinian phase here, and then the later sort of waning pulses at the end. And I'll just note in this figure here, these black lines are showing the peak frequency of the signal through time. And here we see that the 6 pulses sort of have a very similar peak frequency. And then when we hit this long sustained Plinian phase, we see a decrease in this peak frequency that then also remains for the rest of the eruption. And then on the far right, with our spectral curves, we can the colors of these curves match the colors of the detections in A. So we can see this red curve here is that first pulse, and then the green and orange are the later pulses, the later phases. And here we see again nicely highlighted that the peak frequency of those early pulses is higher than the main Plinian phase of this eruption. So we also nicely highlight that decrease in the peak frequency. Now this eruption was also not only observed with infrasound. We saw the satellite images there in the video. The International Space Station also really captured a really nice photo of the eruption here and the far image. And this eruption also put out a significant amount of SO2, which is captured here by OMI instrument on Aura satellite. And then another cutting edge area of research in sort of volcano remote eruption detection and understanding is lightning. And this also had a large amount of lightning associated with it. So this, there was lightning for each pulse, which I'll show you in a moment, but this is just for that main phase, the amount of lightning we see here right over the eruption. So then sort of looking at all of these data together, we can see the infrasound on the bottom with blue is our, where we have robust detections of the eruption. And then we have the strokes per 5 minutes, the peak current of those strokes, our plume height, and then our modeled mass eruption rate, which mostly tracks with the plume height. But here with this eruption, we can see that it turns on. We have 6 pulses that all track that have plumes and lightning, and then this sustained several hours of what we refer to as a Plinian phase, with a large increase in the lightning rate and the sustained plume height. So now let's take a look at Ulawun volcano. Ulawun is in Papua New Guinea, and this erupted 4 days later relative to Raikoke. And this volcano does have population near it. Raikoke is an unpopulated island. And this impacted about 11,000 people for this large eruption. And this one we mostly observe with the IS-40 array near Rabaul. But we also have another array that we detected this eruption with. So here again, so here we see the IS-40, this map here on the upper left, and it was also detected by IS-39, but only just a little bit. It's almost over 2,000 kilometers away. But we got a really good location, just 22 kilometers from True, and this is mostly due to having an array very close, only 113 kilometers away. So here, this eruption, as I said, there are people living on and near this volcano, and we got fortunate. There was a helicopter pilot, volcano enthusiast, out taking photographs of the volcano, and kindly shared his documentation of the eruption that day. So we detect acoustic infrasound signal from the volcano the day prior to the main eruption sequence. So this is on the 24th, and we don't really have much in observations other than the infrasound, which, you know, highlights the real critical nature of having infrasound data, because this occurred at night, and we didn't have any satellite observations. So many things are limited by day or needing daytime observations. And then we have this sort of the second sequence on the 25th to the 26th. And then here again, I'll highlight on the panel B, we have our peak frequency highlighted. And over the course of the eruption, we do see a significant decrease in the peak frequency for this eruption, going into the large Plinian phase again. And then I'll highlight, we had, this was prolific in its lightning generation, which you can see that in the lower left, this large umbrella cloud with a lot of lightning generated there. And then in panel C, again, we highlight this decrease in peak frequency, again, with our spectral curves we see over the course of the eruption. And then bringing it together again. Oh, also, sorry. Also, we confirmed that this first signal that we saw only in the acoustics really is, it points back at the volcano, but you have a bearing and not necessarily a location. But here we several hours after the acoustic signal, we saw a gas signal from an SO2 gas signal with about 5 times the average SO2 output for the last decade. So suggesting that this signal that we see really is a phase of the eruption with a gas signature several hours after it. And then we see a lot more, again, another SO2 detection during the main eruptive sequence. So then, sort of putting this whole time series together, we'll focus on the main day of the eruption, the 25th to the 26th UTC. We see that the infrasound signal in this case starts before we have observable plume and lightning, which suggests, in the other case, we could very clearly see the infrasound onset and the ash, plume, and lightning all happening together. Where here the infrasound starts hours before our ash and our lightning, suggesting a difference in what's coming out of the volcano. Maybe it was very gas rich to start, and then we had ash. So I'll just quickly touch on what we think is happening with that decrease in peak frequency. These types of eruptions are considered volcano jet noise, which is jet noise is a momentum-driven flow from a nozzle. And so this scales, we think scales all the way up to volcanoes, from rockets all the way to volcanoes. And here we have examples from Mount St. Helens and Tungurahua, where we have the spectral curves from these eruptions, as well as the equivalency curves for jet noise. But this is controlled by what those curves look like, and the peak frequency are controlled by parameters of the jet. So the velocity of the jet, the diameter of the jet then influences the frequency we observe. So we have observed a decrease in peak frequency at volcanoes before, but this is the first time here that we have actually observed documented a change in the diameter of the crater, which would suggest a change in the diameter of the jet. So here for Raikoke, this is like SAR amplitude, and we can see the expansion of the crater here, and then in this really nice high resolution images of the Ulawun crater, particularly between A and C, because they have really low clouds, we can see a significant increase in the crater diameter there, which would explain why we get a decrease in our frequency that we observe at the volcano. So this is, active area of research is trying to understand what particularly we're observing. Is it just an increase in the diameter? Is there also an increase in the velocity? Because the eruption intensity increases so much, we would anticipate that both of those change, but we now for the first time have ground truthing of a diameter increase, which is exciting. And so that's all that I have for today. We showed the nice high time resolution that we get from the infrasound. We observed this decrease in peak frequencies for both of these eruptions, which is very likely related to the expansion of the jet expansion and seen as an expansion in the crater diameter. And that's all that I have.
Thank you very much, Dr. McKee. That was really interesting. I hope you will find even more examples that will corroborate your results. That's really encouraging. In an effort, because we have to run to the next talk, I invite everybody to go visit again the presentation of Dr. McKee to post your questions. Don't hesitate. And Dr. McKee, I hope you will be receiving questions and answering them in the chat. And so we'll continue with volcanic activity and infrasound with Dr. Ten, Professor Ten, that is in Singapore and will be presenting live as well. So, Dr. Ten, you have the floor.
Eric. Let's see if I'm have more luck than Kathleen on this one. Can you hear me?
We can hear you and we can see the slides.
All right, sounds good. So yeah, thanks, and traditional good morning, good afternoon, good evening, wherever you are. I will follow up after this beautiful presentation we had on the usefulness of infrasounds to monitor volcanic activity. This work is done in collaboration with colleagues in Singapore, including a colleague that is now back in Vienna and work now at the CTBTO, David Wilton. So this work is based on a few recently published paper. You can pick up your phone, open the camera and snap the QR codes. I will have it at the end of the presentation as well, just to highlight the work that has been done by the team. I think I'm privileged to sit in Singapore, actually. We all heard of Krakatoa volcano, and most of us probably know that it's the loudest sounds ever recorded on Earth. So I will invite you to travel back in time, early morning of August 26th, 1883. You are happily sailing on a boat, and all of a sudden, your eardrums explode with the loudest sound ever recorded on Earth. And I'm talking audible sounds, and you have here, the extent of what has been heard after these eruptions all the way to Mauritius, thousands of kilometers away. Audible. So with this community, you won't be surprised to know that we also have low frequency pressure perturbation that traveled around the globe and has been recorded in Europe, not only once, but 2 times and even further down in time. So this sound travels multiple times around the globe. First ever recorded volcanic events using infrasound. So I love this story, and I'm very privileged to be sitting next to this volcano. This picture is, I think, a potential summary of what Kathleen presented. She presented remote islands with impact to aviations, which is up there. But in these presentations, I like to highlight the fact that when the volcano erupts, the impact of the volcano will evolve with distance, meaning that the time the ash reach a given place, there's actions that can be taken. And I think infrasounds do have a role to play to quickly assess the volcanic activity and trigger mitigating action that can inherently save people and reduce the cost of a volcanic impact. This might be insulting to show in this setting. Those magenta diamonds are the gems of CTBTO. We have infrasound stations installed all over the globe, including regions with dense populations of volcano. So without further ado, I jump into this map, which show you for a given day, we show you the minimum acoustic pressure needed at a location to be recorded by at least one station. The red triangles is kind of a cluster of volcanoes, but what we can see is blue, I can record kind of low activity, and red, I will need higher activity. So those stations are the IMS stations, and if I select a region in Sumatra or a region in the Philippines, this is the time series of multiple years of data, and that's the minimum acoustic pressure needed in order to be recorded. So you can see the seasonality, and you can also see that some of those volcanoes remain in the yellow-red zones, high acoustic pressure needed in order to be recorded. So what if we were to install a station in Singapore? For this particular day, you can see that if I flick between those two maps, we have a blue region on the west of Singapore, so we reduce the minimum acoustic pressure needed to be recorded, which is visible here with the red curves. The red curves is IMS plus Singapore, and the black curve is only IMS. So how do we quantify these improvements? This is for Sumatra. It can be seen as 40% of the time with a station in Singapore, we improve our ability to detect volcanic events by a factor of 3. For the Philippines, which are further away, we improve 20% of the time, we improve our ability to detect an event by 20%. So I think this is the usefulness of a stations, IMS type of stations in volcanically active regions. Singapore is a city-state. I don't know how many of you visit the place. I'm happy to host you next time you visit. The challenge is to find a place to install this infrasound station. But there is, in the middle of Singapore, there is a reservoir surrounded by jungles, and that's where we installed 5 sensors in array configurations. The sensors are MB 2005, will soon be upgraded to MB3A with an overall aperture of 2 kilometers. It's quite fun to go to the field. You need to take a boat, jump in the jungle. So, if you want a bit of the thrill, you're welcome to join to clean some solar panels. So what do we do with these stations? Of course, it's great. We have the, theoretically, we know we will improve the ability to detect, but, in reality, what do we get? So those 5 curves corresponds to the 5 stations, and this, intensity of the infrasounds per frequency band. The good news is we can see here in the low frequency, the microbarom. The dashed line represents the typical high, medium, and low noise level from IMS stations. So we have the good news is we can see the microbarom, which is great. The not so good news is above 8 Hertz is a bit of a mess. We have the station response and anthropogenic noise. If we apply a classic array processing using PMCC, the color here represents the frequency. On the y-axis, you have the azimuth, and on the x-axis, the time. And you can see that the anthropogenic noise is extremely stable, so it's likely to be a fixed source within the country, and wiggling around 180 degrees back azimuth, we have the microbarom. This is great. This is interesting. So if we concentrate on the microbarom, I will switch this view to a map view to get a sense of the challenge. This is actually telling us that, oops, I have a coherent source of noise coming from straight south of the station, which will cover parts of the volcanoes in Sumatra. So here we can see the challenge of, even though I'm close, I might have challenge to detect events nearby. And if I show that in these 3D plots, we have a month on the x-axis, the back azimuth on the y, and the z is the percent of time in which I have microbarom. We can see that over multiple years, overall, I have 4% of time I will have challenge to detect eruption in Sumatra. If I break it down per month, we can see the seasonality, and I think this is important to do when we want to really convey the information that infrasound can detect or not a volcanic event. Right now, This is the microbarom, but when we have an eruption that is loud enough, we might still be able to detect it. And loud enough translates to big enough. And for those who are not within the field of volcanoes, we use a VEI, a volcanic explosivity index. The higher the value, the bigger the boom, if you wish. So bigger the boom, likely to be detected. So if we look at this summary figure from Dabrova et al. In 2012, there is multiple informations. It's quite intense study. What we have in black circles is the most distant detection of a volcanic event from an infrasound station. The crosses are events that were not detected, and open circle are detected. You have on the y-axis the distance from the volcano, and on the x-axis the plume height. The key things that I'd like to extract from here is you can see that anything within 1600 kilometers from the volcano has been detected. So if we keep these informations and draw some circles on a map, here's what we have. The maroon colors are volcanoes that are within 1 hour travel time. Infrasound is painfully slow, so those are 1 hour travel time. The red volcanoes are within 1600 kilometers, and the magenta are not covered by any of those circles. The not so good news is if we look at those volcanoes in Java, they are actually the one with the highest likelihood of producing large eruption in the next 10 years. We have a 50% chance of large volcanic events in this region. So here, I think I take 15 seconds to highlight the fact that international collaborations are key to fill the gaps in those active regions that can be harmful to local populations as well as international traffic, air traffic. To build on what Kathleen just said, when the volcano goes boom, the wave will travel, you will detect it. What you want to do is have an idea of the source and characterize the source, and then you feed that into ash dispersal modeling, hence my questions from the first talk. And we did this exercise. I will use this example from Pertu et al. Last year, in which we look at a few events. So this one is for Sangya Api, 2014. The event was well detected, but what I want to highlight here is back in the day, the stations was not installed in Singapore, but we can see in the bottom of the screen is that Singapore would have been the first station to detect these events. And I think this is also highlighting the fact that IMS-like infrasound stations can help improve the coverage of those volcanic events. So how do we go? I will go quickly. From the stations, we record an amplitude. From the amplitude, I go back to the source. For that, I have a bit of uncertainties in the atmospheric modeling of the propagations. From the amplitude at the source, I estimate an acoustic power. To give you a sense, the Beirut explosions was 10 to the 8 watts, which is slightly below volcanic events, at least in this case. From the acoustic power, further more hypothesis, we derived an exit velocity, and finally, from this exit velocity, we extract a plume height at very great distances, all the way to thousands of kilometers. We have a range of plume heights with associated uncertainties. I really invite you to go and check this paper that will detail all of those. In the last two slides, I'd like to show more examples. We have the Taal eruptions in 2020 with detections all over the place, including Singapore. And here on the right, we have the detections from I-39, beautiful detections for hours, from which we extracted the plume height, which is consistent with satellite measurements, and this information was shared with colleagues from the Philippines in FIVOX that are the colleagues in charge of making decisions and evacuate people. A few more examples. Kelut 2014, from which infrasound can help to extract the duration of the intense phase of injections of ash in the atmosphere. Krakatoa, for which the infrasound detected the events before satellites. The weather was extremely bad, and infrasound detected this intense continuous phase of eruptions before satellites. And a few more examples from the station in Singapore, the Levotolov eruptions, and a fireball that has been observed between Singapore and Malaysia Peninsula. There's blogs on those ones. So to conclude, I really want to highlight the fact that we have how critical IMS-like infrasound stations are to improve the coverage of volcanic activity, reduce the time between the events and the characterizations, increase the level of confidence, have redundancy, and ultimately leading to more time to put in place mitigating actions. Apologize for being a bit over time. I'll leave you with this slide. Happy to take any questions now or in the chat later. And thanks for the convener for organizing.
Thank you, Dr. Tens. That was really nice. Indeed, we'll move on to the next question because we are running out of time for questions. But yeah, please read the contribution and post your questions. There will be ample time for answering questions from Dr. Tens. So thanks a lot. And we'll be moving on to Dr. Marine De Carlo, who will have a pre-recorded video that we will be playing now. That will be about the global microbaroms patterns, infrasound ambient noise modeling versus IMS observation database. So we'll be playing the video, and then I think Dr. De Carlo is in the chat, so she can address questions if we have a bit of time left.
Good afternoon, everyone. I am Marine De Carlo, and I will talk about microbaroms and the validation of the source model through the IMS observations. But first, I would like to thank the CTBTO, the Science and Technology Organization, and particularly the convener of this session, Pierrick Mial, for this opportunity to share the results of my PhD work. Microbaroms are among the sources of infrasound signals detected by the station of the International Monitoring System and are quasi-continuous source of noise for the detection interest of the CTBT. Microbaroms differ from other sources of infrasound by their low frequency, between 0.05 and 1 Hz, by the spatial extension of their sources as they originate from the ocean, and by their ubiquitous presence of the globe. Indeed, as shown in the top right figure, noise spectra present a peak around 0.2 Hz corresponding to the microbaroms, when the local wind is not too important. Therefore, as microbaroms are noise for CTBT purpose, one of the main interests for microbaroms lies in the source characterization of microbaroms in order to better understand the infrasound ambient noise and remove it. The second interest for studying microbaroms is to study the dynamics of the middle atmosphere. Indeed, due to the low amount of direct observation of the middle atmosphere, atmospheric models are poorly resolved at these altitudes, and a proxy is therefore needed. Infrasound signals are a good candidate to be this proxy, as infrasound propagation depends strongly on the middle atmospheric dynamics. Indeed, when there is wind in the stratosphere, around 50 kilometers of altitude, in the direction of the propagation, the infrasound propagation is more effective. Due to the low frequency, in favorable conditions, microbaroms can propagate up to thousands of kilometers, and their ubiquitous detection may allow microbarom signal to be a good proxy of the middle atmospheric dynamics if the source is known. Thus, the objective of this study was to develop a global microbarom source model and to validate quantitatively the source model with global IMS observations. The phenomenon generating microbaroms occur in the ocean. When two wavetrends of similar frequency but opposite direction interact, second-order nonlinear phenomena appear and generate acoustic modes both in the ocean and in the air. The acoustic modes in the ocean eventually excite the crust, generating the so-called microseisms, which theory was first formulated by Longetigins in 1950 and by Asselmann in 1963. When considering an active air layer, the acoustic modes in the air are the microbaroms. The first derivation of Longetigins' equation with an active atmospheric layer was performed by Raikoke et al. 1973 in the case of an infinite ocean. Later on, Waxler and Gilbert 2006 and Waxler et al. 2007 re-derived the equation with an hypothesis leading to a monopolar source. While Waxler et Gilbert 2006 considered an infinite depth ocean, Waxler et al. 2007 refined the model by considering a finite depth ocean and potential resonance of the acoustic modes in the water layer. In 2020, DiCarlo et al. Re-derived the same equations with the consideration of both a non-monopolar source and a finite depth ocean. The maps represent the source model average over 2018 at 0.25 Hz for the source model by Waxler et al. 2007 on the left, which was the more commonly used by the community, and the source model by DiCarlo et al. On the right. The difference between these models led to investigate both of them while comparing with the observations. In order to evaluate both source models, a comparison with observations was needed. As the best observations available are the IMS observations at ground stations, it was necessary to account for the propagation of the signal as shown on the left diagram. For the global modeling, we considered two configurations of the wave model, one with coastal reflection, one without coastal reflection. On this wave model, we applied the source models of Waxler et al. 2007 and DiCarlo et al. 2020. The propagation was accounted for via an attenuation law, and two configurations were considered, one with the wind at the station and one without any wind, for which there was therefore no favored directions. This attenuation was applied to the acoustic source for each model cell. Then, all attenuated model cells were summed by azimuth in order to obtain a microbarom amplitude for each azimuth, each frequency, and each time step. The comparison between observation and modeling was performed for 7 years from 2012 to 2018 for 51 stations of the IMS network, 5 frequency bands, and for the 8th modeling configuration. The observation consisted of the PMCC database of the IMS station as presented in poster 1.1399 by Upe et al. To compare modeling and observations, a direct method is to compare the dominant signal over each time step, which means considering the directions with the maximum amplitude for the model, represented by the blue dots in the upper and lower panels, and the directions of the detection associated with the maximum amplitude for the observation. The maximum among detection over 3 hours is represented by orange dots in the middle and lower panel. Here is an example of the dominant signal comparison between model and observation at I-33, Madagascar. The blue dots are the model dominant signal, while the orange dots are the observed dominant signal. Upper panels compare the model and observed azimuth between 2014 and 2017, while the lower panels compare the dominant signal amplitudes for the same time period. Panels on the left use a model configuration without winds, while panels on the right use a model configuration with wind. The configuration with wind shows a clear enhancement of the dominant signal direction compared to the model without wind. Furthermore, one can also see that the amplitude variations are better correlated when wind is accounted for. On a more global point of view, here we represent the dominant azimuth in color For the observations on the left panel, a model with no wind configuration on the middle panel, and a model with wind configuration on the right panel. For each panel, each line corresponds to a station, and those are ordered by latitude, and the axis represents the 7-year time period of the study. One can note that seasonal patterns are poorly explained without stratospheric winds in the middle panel. On the other hand, while looking at the left and right panel, one can see a first-order agreement in dominant azimuth when considering stratospheric wind at the station. While allowing a visually good representation, the dominant signal method is not interesting for quantitative comparison, as it does not consider the spatial repartition of the source. In order to consider the spatial repartition of the source to allow quantitative comparison, the classification method was used. First, the normalized model was binarized by thresholding. For a given time step, all directions with an amplitude above the threshold were considered true, meaning the model predicted microbaroms arrival in these directions. All other directions were set as false, where the model predicted no arrivals. Then, the predictions were classified based on their azimuth, frequency, and time into predicted observation in gray dots in the lower panel and not predicted observations in red dots in the lower panel. Finally, a metric called CPO as coefficient of predicted observations was defined by considering the ratio between the number of predicted observations and the total number of predictions. This figure presents the CPO metric against the different stations of the IMS ordered by latitude. For the 8 modeling configurations, each configuration corresponding to line. The highest CPO is obtained for the red line, therefore the best results are obtained for the configuration with coastal reflection, with wind at the station, and with the source model of DiCarlo et al. 2020. One may note the high variability along stations, indicating that some will be more interesting to work with for further studies. Another major point shown by this figure is that there is a difference of around 0.1 to 0.15 CPO points between the configurations with the source model by DiCarlo et al. 2020, which are represented by plain lines, and the configurations with the source model by Waxlow et al. 2007, which are represented by dashed lines. The CPO monthly repartition is presented here for both the northern on the left and the southern hemisphere on the center, while the panels on the right represent the source repartitions for January on the upper panel and June on the lower panel. The monthly patterns are quite different. For the northern hemisphere, all configurations have a similar pattern with a CPO decrease during local summer, which could be explained by sources being more scattered and of smaller amplitude during summer, thus more difficult to model. On the other hand, for the southern hemisphere, 2 main patterns are observed. For the configuration without wind, the CPO is globally constant along the year, while for the configurations with wind, there are biannual CPO increases during local winter and summer, where the minimum corresponds to the reversal of the winds when stratospheric ducts are less established and models more poorly resolved. Therefore, the detection at the station is much more dependent on the wind for the southern hemisphere, which could be explained by the source repartitions. Indeed, in the southern hemisphere, as the ocean is dominant, there may be sources coming from all directions, as opposed to the northern hemisphere, where the ocean and continent location makes the sources more localized. Thus, considering the wind is essential to discriminate between sources in the southern hemisphere. To conclude, microbarom sources were characterized by accounting for both a non-monopolar source and a finite depth ocean, and this model was quantitatively validated against IMS observations and proven to give better results than the model that was previously commonly used when accounting for the spatial repartition of the source. Further studies may include implementation of the source model in quasi-real time, sensibility studies to go towards the data assimilation of microbaroms in atmospheric models, or validation of the wave interaction model from spatial remote sensing. Thank you very much for your attention.
And you can hear me. So in an effort of time, we will have to move on. I invite again everybody to visit the presentation and post questions to the speaker, and we'll be moving on to the next talk by Dr. Hooper from Germany. We'll be presenting about the current Infrasound Wavefield, new IMS broadband Bulletin production for atmospheric studies and civilian applications. And I believe it's also will also be played, but Dr. Hooper is with us for addressing questions afterward.
Hello everyone, my name is Patrick Hooper from the German Federal Institute for Geosciences and Natural Resources. In this presentation, I'm going to summarize the results of the latest reprocessing of the IMS infrasound dataset at BGR, and I will provide first insights into specific products derived from the detection lists, as this collaborative project will be finalized soon. What we've learned from earlier analysis and also the previous talk by Marine is that the detection of infrasound from microbaroms well reflects the wind conditions in the stratosphere, as these mainly control the infrasound propagation. In this figure, you can see a first result of our data reprocessing now covering the full period from 2003 to 2020. The first 52 certified infrasound areas of the IMS are sorted from north to south. The background in gray color scale depicts the stratospheric wind conditions at each station on a daily basis. That is the effective sound speed ratio for propagation from west to east. In other words, the lighter the gray, the more favorable is the detection from westerly directions, while dark gray is favorable for signals arriving from easterly directions. And accordingly, we can recognize a semi-annual pattern for microbarom detections within the broadband bulletins. The direction of origin is color-coded as a moving average over about 1 week. Many studies therefore suggest that infrasound can be a passive remote sensing technique for supplementing observational data of the middle atmosphere, and that there is a potential to assimilate these data in weather or climate models. Moreover, it has been demonstrated that infrasound can be used for monitoring natural hazards, such as volcanic eruptions. However, neither the raw IMS infrasound data nor the broadband bulletins as a product are publicly available for such applications. Instead, our idea is to provide tailored open access products of the broadband bulletins. So this results in products of a product, thus not replacing any existing options to access IMS infrasound data or IDC products. At BGR, we regularly update the infrasound broadband bulletins, so these cover more than 18 years now. Recently, we have switched to 1/3 octave frequency bands for the processing configuration of the PMCC method. This results in a better discrimination of sources due to more accurate estimates of the signal parameters. We've also advanced the quality assessment of the resulting detection lists. If you're interested in more technical details, you can have a look at the dedicated e-poster presentation. Moreover, a few studies that make use of the detection lists are presented during this year's S&T, one of which is a presentation given by Marine De Carlo prior to this one. And in the poster in session 2.3, my colleague Peter Gabler presents a study on infrasonic signatures from rocket launches for space missions. As a result of the processing, we have a database consisting of more than 81 million detections over 52 stations. The temporal coverage varies per station, as is shown in the left panel. Okay, one cannot hear anymore the video, I think. Is that correct? Don't know why.
Can you, Patrick, will you take over and continue from there live? Is it possible?
Yes, that's possible, of course.
Yeah, that will be, so we will not play the video anymore. Patrick will jump in.
If I restart, it will stop at the beginning. So if he has the slides,
Yes.
it's
So will he restart or should I take over?
Yes, we will not be able to restart it because we are not sure the sound will come back. So if you can jump in live, that would be excellent.
Yes, just a moment.
Share the screen. Thank you, Patrick.
Oh, sorry for this. Don't know what happened.
Beauty of being on the virtual platform. Perfect. We can see it.
Okay. So, yes. So as a result of the processing, we have a database consisting of more than 81 million detections over 52 stations. I guess that's where the video stopped. So yeah, on the left panel here in this slide, you can see the temporal coverage, which varies per station. And the figure on the right, so this one, shows the number of detections over all stations here. So it's stacked over all stations with regard to the direction and the frequency. Their central frequencies range from 0.02 to 3.5 Hertz, roundabout. And the solid black lines here in this figure depict the frequency bands of the processing. The detections can be differentiated into three groups. That is below 0.1 Hertz with 5% of the total of detections, especially so-called mountain-associated waves. And around 55% of the detections are characterized with frequencies between 0.1 and 0.5 Hertz, including volcanic eruptions and by majority the microbarom detections. Here we can recognize again the global patterns of westerly directions in general and easterly directions again. Although, of course, it's particularly obvious by the peaks here in the right-hand panel for the azimut distribution, that the direction strongly depends on the station location, which is, of course, a bit general here as all stations are combined together. Nevertheless, we have here in the high frequency range more regional and local sources, which is clarified by the peaks. And these include, among others, volcanoes as a natural source. So, yes. For defining data products specific to these categories, we also consider the peaks in the frequency histogram shown in the bottom panel. The first is a low frequency product, particularly for the mountain-associated waves. This will also include other signals, for example, auroral infrasound. Then we intend to provide both a microbarom product covering the spectral peak here at around 0.25 Hertz, as well as one in the upper frequency range of microbaroms and other sources, of course, which is potentially useful for microbaroms from marginal seeds, for example. And finally, we select the high frequency product covering the secondary spectral peak between 1 and 3 Hertz. Each product is defined at equally spaced time steps, either the 30, 15, or 30 or 5 minutes. And the parameters represent the dominant azimuths among the detections in terms of accumulated family sizes within the corresponding time windows. So it's again an accumulation of detections and not each detection by itself. As additional parameters, for instance, apparent velocity, amplitudes, the signal duration, Yeah, and some others are part of the product. For these parameters, all detections from the same dominant azimuth plus minus 1 degree are taken into account. Either is weighted mean by the family size or maximum or sum over all these detections. The standard deviations over all detections within the time window and the number of detections serve as quality parameters for the users. An additional parameter for the quality assessment is calculated, incorporating the correlation coefficient, the Fisher ratio, and the available sensor numbers relative to the array size. The latter because the temporal decrease in available sensors can affect the detection capability and thus the detection numbers or parameters, of course. So let's have a look at two recent events. The infrasonic waves of which were detected by the IMS network. One is the eruption of the Stromboli volcano on 3rd July 2019, here, this column, representing a natural source. The second one is a explosion in the port of Beirut on 4th August 2020 in this column. And here we have the different products we defined, and in this row, it's information about the raw detection broadband bullet. So both events were reliably detected by IS-26 in Germany and also IS-48 in Tunisia, for example, but within different frequency bands. As you can see here, and it's indicated by the green circles if the event is included in the defined bulletin products, and for the broadband bulletins, the frequency is also indicated for comparison. Can we summarize that those products that match the frequency ranges perform well as the events are included same time? Moreover, this shows that the products in the so-called microbarom range also contain further natural and anthropogenic sources. Since this was rather a case study or a few examples rather than a comprehensive validation, recall the global view of microbarom detections from the beginning of this presentation in this slide. We compare this with the same application of the data products. So this is for the broadband bulletins. On the next slide, some data products. Therefore, also please note the differing frequency ranges on the next slides. So here, when using the lower frequency microbarom product, which actually covers a spectral microbarom peak between 0.2 and 0.3 Hertz, we obtain a very similar picture of the semi-annual pattern in azimuth at the vast majority of the stations. So if I skip back, forth again, it's a very similar picture. We have no time for any details here, but in general, we think that this product will be useful for probing the stratospheric winds and advanced applications. When we now switch to the higher frequency microbarom product, we will see a similar pattern at first sight. So now I switch the slide. But at some stations, some azimuth occurs occasionally or consistently. This is particularly striking for IS-30 in Japan, here in this row. I skip back again and forth again. So there's a clear shift in the mean back azimuth. But also other stations in both hemispheres there are differences. So implying that other repeating sources contribute at higher frequencies, or that dominant microbarom source regions in the frequency range differ. For instance, marginal seas or internal seas of limited extent are relevant here. At the same time, these comparisons imply that the lower frequency microbarom product actually represents those microbarom detections that are dominant in the broadband bulletins, as was intended, of course. So to conclude on these insights, we believe that providing Tailored products of the broadband bulletins will be a boost for exploring the potential for enhancing the representation of winds in numerical weather prediction and analysis models using infrasound observations representing the stratosphere, especially if the products will be open access. Specific bulletin products will serve as a reference database for natural infrasound sources, which will be useful for planned and ongoing Horizon 2020 or other projects, for example, the InfraAV project. As a first step, we focus on archived data covering the last 18 years. A related paper is in preparation for submission. In terms of civilian applications for natural hazard monitoring, such as volcanoes, as we have heard a few presentations in this session, next steps towards products being regularly or even continuously updated in near real time would be an asset. Thank you very much.
Thank you very much, Dr. Hoop. I want to especially thank you because you had a difficult role of jumping in mid presentation. So that was really thanks a lot for this. I'm glad you were here live with us. We will have to move on to the next speaker because I realized we are a little bit behind schedule. And so thanks again, and we'll be moving on to the last speaker of the day, Dr. Gonzalo Antonio Fernandez, who will be talking about obtaining the Infrasound Bulletin for ISO 8. So, Dr. Fernandez, you have the floor. Thank you.
Thank you very much. Can you hear me very well?
Yes, we can hear you very well, and we can see the presentation.
Okay, thank you very much. As you mentioned, okay, I'm glad to show the presentation, which is called Obtaining the Infrasound Bulletin for ISO 8. This work has been already performed by the CEA, the French NDC, and our national NDC, Observatorio San Calixto. Well, we all know this is a basic work that we started to do from 2016 to nowadays. So we are some ways below 20 hertz. We have from scientific applications to civil applications. We know that the earthquakes, volcanoes, bolets, meteors, auroras are natural sources. As an anthropogenic sources are also the explosion, rockets, or aircraft that can generate infrasound waves. We all know that we have 60 arrays deployed all around the world, and our station, ISO 8, belongs to the CIADAS. However, it's operated by the National Data Center, which is Observatorio San Calixto. It's installed at the high Andes of the Bolivia and the Altiplano. It's only composed by 4 elements separated 1 kilometers. Our sensors are the MB2000, and the real-time data is sent to our NDC, to the CIADAS, and the IDC by VisitLink. In this slide, I would like to show you our seismic network and the infrasound station, as you can see here on the pointer. It's important to know what are our sources that we would like to monitor. Well, most of the people think that Bolivia does not have earthquakes. Well, sorry for saying that, we do have earthquakes. For example, you can see here shallow. The station is installed here, but you can see the shallow seismicity that can produce earthquakes magnitude above 5, intermediate seismicity by the subduction process between the oceanic plate versus the continental plate, which is Nazca versus South America, deep earthquakes, which can reach magnitudes above 8, and the faraway sources that are from neighborhoods. It's Peru and Chile and almost Argentina. It's all known that in Peru and Chile, they have earthquakes with magnitude above 6 or 7, so we can monitor by the infrasound. Moreover, we have some meteorites or some bolets in Aikile in the central part that were also recorded by the infrasound station. With this context, I would like to show you a little bit of our architecture. As I told you, we only have 4 stations. We have a central facility that the data goes to the French NDC, and the IDC and also to our NDC. We had a donation with the NDC capacity building, which is a server from the CTBTO, where we started to collect all the data. Later on, I will start, then we installed the DTK PMCC, a CTBTO version, and then with the French version. So what was our motivation? We have data available, which is not exploited since 1999 at our IDC. It was offline. We would like to integrate the seismic and infrasound data in the server that we have already installed. And not many researchers have already researched on this topic in the South America. In my knowledge, we have the Brazilian and the Paraguayan NDCs that have some research in this content. However, for my country, especially for Bolivia, there is not many local researchers interested on this topic. With the data of our station, we could see that some peer-reviewed articles were done. For example, the earthquake of Arequipa, a meteorite in 2007 between the Peru and Bolivia border, and the Japanese NDC also performed low-frequency atmospheric gravity waves with the two mega thrust events in 2010 and 2014. So we would like to start developing some bulletin to help other researchers or to enhance our research production in my NDC. So our methods are basically the capacity building training. We took the basic one in 2019. We also were engaged in the Latin American Caribbean Regional Infrasound Workshop. We set up the environment, which is the DTK PMCC and the donation of the CTBTO on the server. And we started to look at the European Bulletin, Infrasound Bulletin as an example, and also the IRIS that had some products related to infrasound. So our first method was, we call it TRY, from 2016 to 2018, where we were searching and looking for CTBTO bulletins, the RLB bulletin, LLB bulletin, and also from the regional bulletins and some volcano alerts from our neighborhood countries, from Peru and Chile. However, we only could find a few seismoacoustic events, and we were not able to find all and know the sources of infrasound. Since 2019, and after the training, we decided to install inside the server the DTK PMCC. So we have the continuous data from ISO8 station. We installed the PMCC and we installed the DIVA. We started to perform a monthly detection. We started to look for some atmospheric variations, and we also have some earthquakes and volcanoes. This allowed this method constant that we call allowed to have data from 2014 to the last year, 2020. So with the test environment, we learned how to work with the PMCC and DIVA. We could study specific events as a meteorite in Chile, but with the constant, we prefer to keep on with the constant method. We can hear all events catched by the in-station infrasound station and try to produce a bulletin. As a result, I would like to show you that from 2014 to 2020 in November, we could reach some variation, atmospheric variation, as I showed you, and we started to try to categorize them. For example, you can see here clearly that we have some detection here, but it was interesting when we start to look at the azimuth and the infrasound velocities with this seasonal variation, as you can see. And here we note in 2019 that we started to have more noise that can be due to the expansion of the city, or can be some noise that is not unknown yet for our NDC. But we could manage to know that these azimuths and these frequencies belong to the microbaroms on the Pacific Oceans. The azimuth is well constrained, and we read on some papers, as I was looking on your presentation, we can say that those detections and seasonal variations belongs to the microbaroms that we represented that we can hear from our station. For us, it was like a great goal. It's a small goal, but at least we could manage to install the software and to detect some variation. Here is the meteorite, the Aquile meteorite that I show you. We worked in this project with the CIATAS, with the French NDC, and we catch the azimuth very clearly. So we said that this small meteorite, which was not a big one, was catched by our infrasound station, that we can work with a lot of data, but we need to categorize. Well, as a discussion and to end the presentation, the CIADAS and the Observatory San Calixto has a well-known collaboration for more than 40 years that allow it to exchange our knowledge, and it's a good example of NDC collaborations. This is the first stage of our bulletin. We noted a clear the microbaroms from the Pacific Oceans, but we know that we need to have more research from medium to long term to try to categorize some GT events to strengthen knowledge and collaboration with the Paraguay NDC, that also they have some work peer reviewed on international magazines. So we would like to also to improve and to enhance our knowledge in infrasound. So thank you for all. I'll be glad to answer some questions. Here you have our main webpage, which is all the products that we present, our Twitter, our Facebook, and I'll be glad to answer the questions. Thank you very much.
Thank you very much, Dr. Fernandez. That was really interesting. I'm very glad to see what the work you have accomplished recently with the re-exploring the Bulletin and the data from the IO8 Bulletin station and the large efforts you've been taken on board recently. That's really excellent. I would like to ask a couple of questions because there's a couple of minutes we can use. I'm just curious, have you looked at the reason, what could be the reason for this change of behavior in the station, which I think could not read very well on the slide, but I think it was around 2019 that you had a change from a limited number of detection to a very high number of high frequency detections. Was there a change at the station, or do you think it could really be the expansion of the city? Because it looks very sudden. So I was thinking that if it's an expansion of the city, it would be more progressive. And this sudden change would make me think of maybe there was someone else that just changed. Do you have any ideas?
We have some clues. We used these small stones to cover the inlets, which are the natural filters for the winds. This small stone started to be, let's say, humid because of the heavy rains. This can be one reason. Since 2019, it started to rain a lot nearby to the infrasound station. We also had a problem with some flooding. So this is just one clue. We're asking the permission to CTBTO to change these small stones, the natural filters. And then we noted that there's some concrete enterprises started to install a few kilometers away from the stations. But as I mentioned before, we need to categorize and also to ask to the French NDC that has a lot of knowledge in this topic to let us know what was the reason of the change of the behavior of the station, which we noted is more noisy nowadays.
Okay, excellent. No, that's I think you have a very good point, and I encourage you to continue looking into this this change. Maybe there is something to fix, or maybe there is a change of behavior is expected. But it will be interesting to know the reason. Since we have to conclude now, I want to add one more comment, because I'm really happy to see that you are planning to reach out or have reached out to the Paraguayan NDC as well to look into maybe building some kind of regional capacities. I think it's an excellent thing. What you are looking at, these European infrasound bulletins, looking at a similar activity in Latin America, that's a very good idea. So I hope the colleagues from Paraguay are listening, and maybe even colleagues from Chile, and they will be inspired by this, even from Ecuador with the station in the Galapagos. But yeah, I encourage you to continue these activities. So I think we will need to conclude now. So we didn't have so much questions to ask the presenters from the chat. It's been a little bit quiet because we were so busy with all the presentations. But I encourage everybody who's watching the replay later to go visit the contribution that are accessible through the program. Today's 01.1 oral session, and then you can post your questions and vote. So because I think it's important to vote for your preferred oral presentation as well as the posters. So I encourage you to go visit the material available revisit it, rewatch it if you want. The recordings will be available soon. And one more thing that I encourage you to do is, if you want to discuss with each other, between authors or with participants, go visit our video rooms and go meet each other and continue the discussion. I know yesterday, after the e-poster roundtable where T1.1 was featured, there was a good group going there and discussing. So if you want to discuss with each other, I encourage you to do it. And otherwise, I just want to thank you all the presenters, to thank Paulina Bittner with me for hosting this, the technical team that is with us here to making sure it runs smoothly, especially when we have a few glitches, and the speakers again, because you've been excellent, and despite all these technical glitches, we made it through, and you've been really good. So thank you for accepting this, and I wish you a nice day, a nice evening, a good night, wherever you are, and especially to those that are in a very different time zones. Yes, good night. Thank you very much, and have a good day, and continue to visit the posters and the presentation, please. Bye.